Biorefinery System Module 11 Lignocellulose Biorefinery Process Engineering Part 1 Segment 2 Transfer in Solid-State Fermentation with me Yusuf from Bioengineering Study Program, School of Life Sciences and Technology, Institut Teknologi Bandung. Previously, we have discussed about transfer in porous media. In this segment, we will discuss about transfer in solid-state fermentation. The solid-state fermentation system is one of the most typical porous media systems. It contains the solid body, aqueous solution, and gas phase, and involves moisture and heat transfer. Heat and mass transfer properties of the medium have a great deal to do with the moisture content of the medium and energy types of water in the solid-state fermentation system. When studying heat and mass transfer in the matrix, the substrate is divided into three categories based on the amount of moisture in the substrate. Water content is 100%. For example, the pore space is filled with the liquid water. Second, moisture in the presence of liquid and gases formed in the non-saturated matrix. Only moisture vapor appears in the pore space of the dry saturated matrix. In most cases, the substance is unsaturated multi-phase system containing solid particles, water, steam, and air. Water vapor transfer mechanism. Transfer mechanism of water involves discussion about free water, bound water, and oxygen supply in the solid-state fermentation system. In order to model the water distribution of the sprayed water throughout the mixed substrate bed, there are three different processes that need to be considered: external addition of water to the particles, absorption of water by individual particles, and transfer of water between neighboring particles. Diffusion mechanism of vapor. Diffusion of vapor in the matrix has a very close relationship with the internal structure of the matrix, and the shape, size, and the gas density of the internal pores determine the diffusion mechanism. Movement of gas phase in the substrate. In the non-saturated matrix, gas is mainly composed of air, water, vapor, and air and water vapor fill the pore space. The migration of the gas in the matrix is of four types. There is Knudsen diffusion, viscous flow, continuous diffusion, and surface diffusion. Heat transfer mechanism. The heat migration of internal particles involves three common forms. First, heat conduction. When there is a temperature gradient in the substrate, heat is transferred by heat conduction in solid matrix, liquid water, vapor, and air. Convection. Convective heat transfer is caused by flow of liquid water, vapor, and air within the pore channel of the matrix. Third, phase change. Liquid vaporization and vapor condensation may occur on the liquid surface within the matrix because of the temperature gradient, which produces heat by phase change. For more details on the transfer mechanism of heat and water in solid-state fermentation, students may refer to Lignocellulose Biorefinery Engineering Principles and Applications, authored by Chan et al. 2015. Theoretical model of heat and moisture transfer. Researchers have made considerable progress in theoretical studies of water movement in unsaturated or saturated porous mixture under isothermal conditions. The early studies have shown that under non-isothermal conditions, the distribution and changes in temperature in the matrix impact the physical and chemical properties of the matrix water and subsequently affect the matrix potential, solid potential, and hydrodynamic parameters. These parameters affect the fermentation temperature. Therefore, in the study of water and heat transfer, researchers should highlight the mutual coupling relationship between them. In a brief introduction to the theoretical model of water and heat transfer in porous media under non-isothermal conditions, the Philip and de Vries model presented water and heat coupling migration that take into account the liquid-gas two-phase flow and the water content and temperature gradients at the same time. Because of the wide applications of the theory of Philip and de Vries, it promotes the combined study of water and heat transfer in the matrix. For more details on the model, students may refer to Cellulose Biorefinery Engineering, Principles and Applications, authored by Chen et al. 2015. Heat and moisture transfer process in moisture stratification. Solid-state fermentation substrates are typical water-unsaturated porous media. However, in some cases, water is seriously lost and utilized as well as strong ventilation in the fermentation process, and the surface water will be depleted, resulting in the usage of the water inside the pore. When the water inside the pore is also dissipated completely, the substrate will form a dry saturated layer. After the dry saturated layer forms, evaporation does not take place on the surface of the substrate, but only inside the matrix. The moisture evaporation intensity decreases, and the loss of matrix moisture is controlled by diffusion from vapor to air, and it is related to the thickness of the dry saturated layer. Therefore, the study of the actual system must also consider the impact of moisture stratification on its internal heat and moisture migration. Effect of temperature on the heat and moisture content in a solid matrix. Essentially, the temperature changes affect the physical parameters of the matrix. It has been reported that there is a positive correlation between the temperature and the matrix water potential according to capillary theory. The water suction of the porous matrix decreased with the increased temperature, and there is improved water potential and water energy. Preliminary studies showed that with an increase in temperature, the moisture transfer accelerated. The changes in temperature can also cause differences in the density of the water vapor and subsequently cause the movement of water vapor. In addition, temperature variations will affect some physiochemical properties of water, such as viscosity, density, surface tension, and so on, which affect the water potential and water movement. Temperature greatly affects moisture movement. For the water-soluble organic salts and organic nutrients, the diffusion coefficient of the solute is also associated with temperature. For example, the diffusion coefficient of sodium chloride in water at 35 degrees C is twice that at 5 degrees C, indicating that temperature largely affects the diffusion of salt. The fermentation substrate is a porous medium, while diffusion of salt in water is different to that in a matrix solution. Thus, the impact of substrate water content and matrix polytortuosity factor need to be considered. For the next segment, we will discuss about heat and moisture in steam explosion process. Until then, I am Yusuf from Institut Teknologi Bandung.